Welcome to our final presentation. This project aims to design a drone that maximizes flight range by optimizing the three subsystems within the system boundary: propulsion, frame, and battery. We are not optimizing outside of the system, but external factors will impact our optimization. Interactions between subsystems and external factors are shown in the figure. There are several coupled variables: propulsion dimensions, propulsion weight, and frame dimensions, as well as several shared variables: package weight, package dimensions, and battery weight.
The design variables considered in this optimization include 82 different propulsion combinations, the forward speed of the drone, the dimensions and materials which make up the structural beams, 16 different battery options, as well as how many batteries will be on board the system. In addition to the design variables, a number of fixed parameters were included in the model. These describe known quantities such as the package dimensions and weight, a miscellaneous buffer mass for unmodeled components, and the minimum allowable drone speed. To ensure realistic and feasible outcomes, the model also includes a set of system constraints, which are shown here in negative null form. These constraints limit the total drone weight, propulsion current draw, and thrust, while also enforcing geometric and structural limits, including minimum frame dimensions, maximum allowable beam deflection, and von Mises stress. Additional constraints were included for battery volume, wall thickness, and the allowable battery weight range to ensure compatibility between subsystems and to help guide the optimizer toward a valid local optimum. To further define the model, multiple side constraints were required, including the drone speed range based on possible propulsion systems, possible frame dimensions based on the propulsion system dimensions, and the number of batteries options considered. The objective of this system-level model is to maximize flight range, as shown by the equation at the top. Achieving this goal involves navigating trade-offs across several subsystems. For example, a larger battery can store more energy and extend range, but it also adds weight, which increases power demand and may reduce range. The same trade-offs apply to choosing stronger frame materials, larger propulsion systems, or adjusting frame dimensions. Each design decision pulls in multiple directions, making it a delicate balancing act. This is exactly where optimization models add value. What makes the system-level optimization different than the subsystem models is that here, all of these design parameters are linked. In subsystem models, they were treated independently, but now, decisions in one area, like frame dimensions or tilt angle, feed into others, such as the drone's frontal area, which impacts drag and ultimately determines propulsion needs. By coupling these variables together, the model allows us to find a more realistic and truly optimal system configuration.
Analytical modeling methods were utilized to optimize the drone. Optimization began by determining the maximum capacity of potential drone batteries over a range of weights, 2 to 9 kilograms. Capacity of batteries configured in parallel can be represented by equation 1. Maximum battery volume was fixed to ensure that it can be packaged in the frame. It is assumed that voltage and current are constant and that all batteries have the same voltage. These packaged batteries are then provided to an all-in-one model of the propulsion and frame subsystems, which optimize battery selection for overall flight range. The all-in-one model then determines frame dimensions and materials for the drone's H-frame. The frame's middle beam was modeled as a simply supported beam with a total load acting in the center, calculated using equation 2. This force calculation is necessary to evaluate the previously discussed constraints that ensure the frame is sufficiently rigid. The weight of the frame can be calculated utilizing equation 3. Next, thrust required for the drone's flight is calculated. We initially assume that the drone operates at a pitch angle of 0 degrees. We assume that the drone can be approximated by a cube and that a cube's coefficient of drag and tilt angle are linearly interpolable. Coefficient of drag can then be calculated utilizing equation 4. Pitch angle is then used to calculate the drone's frontal area as shown in equation 5. The maximum length of the drone is either the beam or package length, whichever is larger. Required thrust is calculated with equation 6. Wind and ground effects are not considered, and the drone operates at a constant speed. Actual drone pitch is calculated utilizing equation 7, which is compared to the previous value. If these pitch angles are not equal, these calculations are repeated with the new angle until the previous and new pitch angles are equal. Leveraging the calculated thrust and the propulsion system's efficiency at the desired drone speed, power can be calculated as shown in equation 8. Power can be converted to current utilizing propulsion voltage, shown in equation 9. Finally, current battery capacity and drone speed can be used to calculate the maximum range of the drone, the objective function of the system. It is assumed that propulsion is the only load on the battery. Voltage differences between the battery and the motor are resolved by the propulsion system's electrical speed controller.
We chose to optimize our system using MATLAB's genetic algorithm. This method was selected for its ability to use integer design variables, aligning with our discrete design options. Additionally, the fact that our design variables are well bounded allowed the genetic algorithm to work well for our use case. To ensure the solution space was sufficiently explored, we leveraged different creation and crossover functions to create the initial population and then form different crossover children. This was on top of MATLAB's internal RNG. Our initial optimization runs showed severe variability in our results across the different population conditions. This can be attributed to our system's large search space, created by the quantity and bounding of our design variables. To reduce this variability, we refined our design variable boundaries to more tightly surround the highlighted optimal value found in the table. Our refined optimization results in the table show significantly reduced variability. Among this batch of potential combinations, we found our optimal solution at the first set of population conditions, shown highlighted in the table. This drone design utilizes propulsion system 4 and travels at 25 miles per hour. It has a frame made of carbon fiber reinforced polymer with the shown beam conditions. And then it utilizes 3 of the battery type 5 wired in parallel. The final drone weighs 9.7 kilograms and has a maximum range of 125.5 kilometers, significantly exceeding our team's original target of 10 kilometers.
All system constraints and parameters are relisted on this slide. The variable values that correspond to the refined system optimization from the last slide are shown in the rightmost column here. If these values are within 10% of the original constraint value, then they are considered to be an active constraint. This includes max drone weight, minimum beam width, minimum beam length, and minimum frame wall thickness. Since there were 6 parameters in the system, 3 were chosen for sensitivity analysis. They are package weight, density of the air, and minimum drone speed. The same 6 combinations of crossover and creation functions used in the system optimization were tested again for each active constraint parameter. The highest objective function value, positive and negative, were chosen out of the set. As recommended in class, an alpha of 0.1 was tested on each parameter and constraint. While many could produce outputs with an alpha of 0.1, it was found that the maximum drone weight was intolerant of an alpha greater than 0.08, and minimum drone speed was intolerant of an alpha greater than 0.07. Alphas of higher value would result in no solutions that satisfy all system constraints. All 6 combinations of testing maximum drone weight with an alpha of 0.08 are shown below. In this case, the chosen objective function values are highlighted in green, and the resultant sensitivity is shown in the bottom left. The results of testing all constraints and parameters described by the methodology on the previous slide are shown here. It was found that maximum drone weight was the most sensitive active constraint in the system, and density of the air is the most sensitive parameter in the system. It can be observed that decreased weight led to a significant decrease in range, implying that drone range is quite sensitive to changes in weight. However, increased weight led to similar results to the original constraint, suggesting that the selected constraint is not limiting the drone's maximum range. It can furthermore be observed that changes in range due to air densities did result in differences in range, but the differences were small. It could be that the system is less sensitive to this parameter, or it is possible that the results are being obscured by noise inherent to the solution of the genetic algorithm. Further runs and filtering could improve the certainty of this analysis.
Here we compare the key results of our optimized drone to an Ares X900 drone. The drone weights, payloads, battery selections, and lengths all match closely, indicating that the 2 drones are similar and we would expect them to be comparable. As can be seen, for a flight speed of 25 miles per hour, our optimization yielded a 125.5 kilometer flight range. For the X900 traveling about 3 miles per hour slower, it is only rated for a 19.8 kilometer flight range. We expect this vast discrepancy in range to be due to our model not taking into account any variation in speed, wind or ground effects, as well as any additional power draw from other onboard electronics, such as cameras or LiDAR.
After optimizing our drone as a full system, as shown in the table, we managed to increase our total flight range achieved from 35 kilometers up to 125.5 kilometers. Our main takeaway after optimizing as a full system for the final report is that our initial value assumptions, such as weight allocation, were far from optimal during the interim analysis. For instance, we need to be sure that the battery is providing the maximum capacity to the overall system. In the interim analysis, the battery was allocated 6 kilograms. Post-system optimization, weight was reallocated from the subsystems to allow the battery 7.8 kilograms of drone weight. This additional 1.8 kilograms increased the battery capacity by 23 amp hours, drastically impacting our drone's total range. This, coupled with the other modifications listed in the table, gave us about a 3.5x boost in flight range.
The model selected propulsion system 4 due to its high efficiency and low weight, since the power required to increase drone velocity scales quadratically, while range increases linearly. Flying faster than 25 miles per hour would reduce total range. Reinforced carbon fiber, though slightly denser than the other materials available, has a much higher Young's modulus and yield stress. This enables a lighter and more structurally efficient frame compared to plastics or metals. The model also showed that using either a lighter or heavier battery significantly reduces range, emphasizing the system's sensitivity to battery weight. To improve the model's realism, several extensions could be considered. Currently, the only objective is to maximize range, with no consideration of cost, a critical factor in most real-world applications. Incorporating cost as a constraint, or as a weight term in the objective function, would make the optimization more practical. Structural constraints could also be expanded to include torsional stresses, better capturing the real-world loading conditions of the H-frame. More detailed material failure models, such as delamination or fiber rupture in carbon fiber, and the absence of an SN curve for aluminum, could shift the optimal material choice. Finally, the assumption of constant velocity simplifies the flight profile, but modeling variable velocity, especially during takeoff, would yield a more accurate prediction of drone performance.
This concludes our presentation. Thank you for your time and attention.